So we continue on the topic solution of ODE differential equation using the Laplace transformation. We looked at one particular example of second order ODE, which was some sort of k over tau 1s plus 1, tau 2s plus 1, C1is. So if you recall, this is the chlorination example that we looked at, and you saw that for the C1is of the form m over s, we ended up getting this solution to be now if we look at this solution is not valid for if tau 1 equals tau 2, this term is infinity and this term also becomes infinity. Okay, now for tau 1 plus tau 2, simply is this not valid simply because the partial fraction expansion method that we approach is not valid for the case when tau 1 equals tau 2. Now if tau 1 equals tau 2, a general equation can be written as ys equals k over the tau s plus 1 square us. Okay, now if we take an us, again m over s, so we can write ys to be km over s tau s plus 1 squared. Now to take the inverse Laplace, we need to express this using partial fraction expansion. For this case, when you have the square term, partial fraction expansion are written as squared. Now to find the value of this a1, a2 and a3, we will write then km equals a1 and to find out the value of a1, a2 and a3, just simply put, we get km a1. If we put s equals negative 1 over tau, we'll get km equals now if we equate the s squared, on left hand side there is nothing, right hand side there is, this will be tau squared s squared, so a1 tau squared, this one will be a2 tau s squared, so it will be a2 tau, and there is no square term here, so we'll have from a3 being negative km tau, a2 will be, so now from this here, a2 being negative a1 tau will be negative km tau. So we'll have now ys equals this term, so ys will be a1 being km, so km over s, a2 being negative km tau over tau s plus 1 minus a3 being again negative km tau tau s plus 1 squared. Now we know the inverse Laplace of this term, we know the inverse Laplace of this term, we don't know the inverse Laplace of this term. So let's just use the common expression for inverse Laplace of this term, 1 over tau s plus 1 power n. For a general term, something like this, we'll have tau n minus 1 factorial t n minus 1 exponential negative t over tau. So for n equals 2, we'll get the inverse Laplace of this to be squared to be 1 over tau squared t e to the negative t over tau. So now if we take the inverse Laplace of this entire term, we'll end up getting yt km being there in each term. We'll take this to be out of the, and 1 over this will be again 1 minus tau over tau s plus 1 will be e to the power negative t over tau, and then this one we know that we'll have 1 over tau squared t e to the negative t over tau will end up being t over tau e to the negative t over tau. So you can simplify it further as km 1 minus e to the negative t over tau 1 plus t over tau. So that's the expression for yt when the transfer function between y and s is given by this function, and for us being 1 m over s, meaning a step function with a magnitude of m. Okay. Now in general, so we have seen this one form of second order model, the second form second order model. In a general form, we can write a second order model to be, suppose if I write it as a2 d square yt plus dt square plus dyt dt plus a naught equals b ut, suppose for this case. Okay, we can express it this way, or you can have in the Laplace domain we can write ys equals, suppose b over a2 s squared plus a1s plus a naught us. Okay, in the so-called standard form, this is written as using notation k, and this coefficient, whatever, now we can divide it everything by a naught to make this to be 1. So this last term is written as 1, and a2 over a naught is written as something like tau squared s squared, and this a1 by a naught term is expressed as twice xi tau, and s remains there. Okay, so this is what is called the standard form of this second order model as a transfer function. Okay, now second order, again, for a differential equation, the order of the differential equation is nothing but the highest order of the derivative term. The same in the Laplace domain, the order of a transfer function is the highest order in the denominator of the transfer function model. Now for this case, if we have 1, we end up getting this model. So if we simply put it xi equals 1, tau square s squared plus twice tau s plus 1 becomes tau s plus 1 whole square. So you get k over tau s plus 1 whole square, this transfer function. Okay, now if we have greater than 1, you end up getting this type of model. So if a value of this xi to be greater than 1, you can factorize it into get something like this one. It will be k over tau 1 s plus 1, tau 2 s plus 1. Meaning that this polynomial will have some real roots here. You see that the solution of s here is s equals negative 1 over tau 1. Here is negative s over tau 2, have some real roots. But for when you have this between 0 and 1, this will have what is called an imaginary root. Okay. Now that brings to some important discussion we talked about when discussing about this Laplace transformation. We said that when there is, like in the s term, there are real value and imaginary value. When it's real, that represents that there is an exponential term in the signal. So you see here, we said for both of these cases, the value of s is real. Okay, and we see that in both of the responses, the responses has done exponential term here and also here. Okay, and we also said that when this s, the Laplace operator has a value of has both real and imaginary part, it says that there's some sinusoidal component. Okay, now what happens when xi is between 0 and 1? We have this real plus imaginary component, so you see that there will be an exponential term and a sinusoidal term there. So without going to detailed, for this case, I will just write down the expression for yt. What happens if I take this inverse Laplace? Okay, so for xi between 0 and 1, we'll have yt km, again 1 times cosine tau t So you see that the expression becomes a little bit involved with both exponential component and the sinusoidal component. Okay, so try to relate it to the basic definition of this Laplace transform. What is said that okay, the Laplace transform can identify both the sinusoidal and the exponential component, and here we see an example where we have for this, when the root has both real and imaginary component, we end up with an expression having both exponential and sinusoidal component. Okay, so that's the solution of ODE in general for second order linear ODE differential equation model.